So we're ready for our feature event. We are honored to have Dr. Roger Jones with us this evening, talking about hurricanes, climate change, stronger storms. We know, obviously, on our position on the Gulf of Mexico here, we're in a vulnerable area. When you look at the map statistically, I think it's pretty much us, and down around Miami gets statistically is most likely to get a hurricane in any given year. So it's important for us to know how the basic processes of how hurricanes work, and then also how they're forecast to change and predicted to change as our climate changes. So that's what we asked Dr. Jones to come and talk to us about. He's actually a native of Pensacola, and he's back now after being away for many years. He spent a lot of years. First, he left to go to Dartmouth, got trained in physics, and spent a lot of years out at Los Alamos National Lab out in New Mexico, the wonderful state of New Mexico. And today he's a research fellow at the Center for Complex Systems and Enterprises.
Correct, yeah.
At the Stevens Institute of Technology up in Hoboken, New Jersey, where he spends a good deal of his month, so back and forth between there. But we're really honored to have you here, and the floor is yours, so thank you.
Okay, thanks, Christian. I'm very happy to be here. Thank you, Christian. Thanks, Elaine, for inviting me. I'm not a climate scientist, and I don't know that much about hurricanes, so I'd like to say a few words about how it is I'm standing up here at the moment. What I'm going to talk about tonight is an excerpt from a book that I co-authored with John Cassidy and Michael Pennick on social events, not just social events, but extreme social events, and how human beings and societies navigate through extreme social events. Now, what might an extreme social event be? It might be a hurricane event like Hurricane Sandy that's disruptive of infrastructure. It could be a war. It could be an asteroid strike that causes some problems with the biology. Or it could be a financial crisis, or it could be something as simple as a road blockage. So anything that comes on fast and unusual, that causes a disruption in human behavior, that's what we were interested in, what we wrote this book about. As we were doing the research for the book, what became apparent was that many of these social phenomena have analogs in nature. And what we discovered is that formation of hurricanes turns out to be a good analog for many social extreme events. But I'm not here tonight to talk about the extreme social events. That's a topic for another occasion. But I am here to talk about the formation of hurricanes. So I am a physicist. I'm coming at this new. I probably approach this in a way that is different than what you're accustomed to because of my background as a physicist. So what I'm going to do is tell a story. Now, the great mythological, or the great mythology scholar, Joseph Campbell, pointed out that human beings don't learn or change their behavior or make decisions unless they can tell a story about why they're doing it. This is in large part why we have this large tradition of mythology, among the human race. If you present data and facts and information, as many of you know from interactions in this political climate now on Facebook, facts are irrelevant. Data is irrelevant. Stories are important. So rather than show you or base my whole talk on a great deal of facts and figures, I'm going to show facts and figures. We're going to talk about science, but I'm going to talk about it in a mythological context. I'm going to try to create a story, and then we'll see how the science fits into the story. I took on the exercise of trying to make a creation myth. not any creation myth, but a scientifically accurate creation myth for the formation of a hurricane. And so here it is. I'm gonna run through the creation myth. I'm actually gonna turn around and read the slide, which is a big no-no, but I'm gonna do that anyway. And I'm gonna go through slowly so we can get the sense for the story that we're gonna tell. Okay, so it's the creation of the great hurricane. In the beginning, you always have to start a creation myth with a t equals 0 in the beginning. In the beginning was the calm. The air sat upon the sea and land and did not move. The temperature here was the same as the temperature there, and the sunlight penetrated the air as if it were invisible. The sunlight struck the sea and heated it. The temperature was no longer the same here as there, and the sea became hotter. And great rolling, boiling winds were formed from out of the calm. Okay. The winds captured the heat from the sea and carried it high into the air. And the earth began to spin, dividing the wind into 3 parts. And the sea continued to heat. And near the equator, there was a dip in pressure, and the wind rushed in, but the spin kept the wind at bay. And the wind pressed harder until a great cyclone was formed. And the cyclone carried heat from the sea to the sky, and the wind blew the cyclone from east to the west, and 2 gyres came as the heat was released. Okay, this is getting pretty complex. And the rains came harder, and there were thunder and lightning, and the land filled with water and slowly drained into the sandy soil. I made sandy soil in honor of Pensacola, and met with the great underground river that flowed to the sea. And then the cycle starts over again, and the sunlight struck the sea and heated it. Okay, so that's what we're going to talk about, but I'm going to hang some science off this as we go forward. First thing I'd like to talk about is a cornerstone of physics. It's called the second law of thermodynamics. Basically, this is where existentialism meets science. It means there is no hope. The universe will end in a great heat bath where there is no deviation and no order. It's very dismal. Physicists are very dismal. But what this means in our practical sense is that any closed system, and I'll describe what closed system means, will try to equalize its temperature throughout the system. That is, any closed system will try to come to thermal equilibrium, where the temperature here is the same as the temperature there, throughout the system. Now, basically, the Earth and the area around the Earth is not a closed system. It's what's called an open system. And the reason it's called an open system is because there's an external energy source that dumps energy into our Earth system. This biggest energy source is, of course, the sun. However, if we take both the Earth system and include the sun in our system, then we are talking something that's very close to a closed system. Eventually, the Sun-Earth system will decay into a meaningless heat bath. It will be a thermal equilibrium throughout some large region of space. Okay, so very dismal. Okay, Billy. Yeah, we should be worrying. You should be worrying. It'll only happen in the next 18 or 20 billion years. So we're okay until then. So let me talk a little bit about atmospheres, enclosed and open systems, and thermodynamic equilibrium. Let's think of the simplest possible atmosphere we can. Okay, here's a bunch of air, okay? And here's the sun. The sun's shining light through the air, and this is probably the sea. Could be land, but Earth is mostly sea. And the energy from the sun is heating up this bottom layer of the atmosphere, or it's heating up the sea, and the sea is hotter than the temperature at the top. So this is a closed system, if we include the sun, but it's not yet in thermal equilibrium. The sun is very, very hot. The sea is a little bit hotter than the top of the atmosphere. So locally, this system will try to achieve, as best it can under these conditions, thermal equilibrium, where the temperature is the same everywhere. So what does that mean? Well, what it means is heat, here's the concept, heat, which is a kind of energy, has to flow from the hot spot to the cold spot. Heat is a very special kind of energy. Heat is energy that's composed of the random motions of molecules, or electrons in atoms, or electrons in metals. It's a very random kind of energy that involves molecules or small particles banging into each other. So what this means is, down at the lower atmosphere, since it's hotter down here, the molecules in the atmosphere are banging into each other harder than they are at the top of the atmosphere. So how is heat transformed from the bottom to the top? Well, these molecules start banging into layers higher and higher in the atmosphere, and they start transferring their energy to these slower moving molecules. And eventually, if we wait long enough, and this atmosphere were a closed system, the molecules at the top of the atmosphere will be banging into each other just as hard as the molecules at the bottom. They'll be moving around randomly in the same manner as at the bottom. So heat, according to our second law of thermodynamics, heat is this random energy, flows from the bottom of the atmosphere to the top of the atmosphere. Okay, it's pretty simple, you know. But if we look at that, we say, you know, our own atmosphere is a little bit more complex than this. Why? Well, why? What is happening is that if we heat this bottom a little hotter than it is right now, just heat it some more, heat's going to have to flow faster from the bottom to the top. Well, nature, being clever, decides that if at some point this temperature gradient is so large, gets very large, it will suddenly completely change the way that heat is moved from the bottom to the top. So what happens is, if the sun is a very weak sun, we get this very simple atmosphere, not very exciting. But our sun is not very weak, it's stronger, so this heating is greater, and as we increase the temperature, suddenly we see a new effect appearing. Now, this effect has a great name, which I love to say, and most of you probably have not heard this name before, but what happens is called Rayleigh-Bénard convection. And you can see this, and you see it every day. in your kitchen. If you take a skillet, put some water or other liquid in it, heat the bottom of the skillet, before the boiling starts, you will see this kind of rolling motion in the fluid. This rolling motion makes these little cells, which you see right here, and the physicists never use, something as simple as little cells. They call these things Rayleigh-Bénard cells, after the instability that causes them. So this is what happens in our own atmosphere. The heating of the surface of the Earth is great enough so that it creates these Rayleigh-Bénard cells. And if you look at your experiment in the kitchen, these Bénard cells will fill up the whole, this whole skillet with this rolling kind of convection. That's what happens on a global scale to the Earth's atmosphere. So here's the Earth, or a, elliptical version of the Earth. The aspect ratio of the projector is not the same as the computer. So what we have on the Earth are these rolling Bénard cells. And in fact, from the equator to the North Pole, there are 3 of these rolls. The lowest roll, just north of the equator, I mean, this is all mirrored in the south too, but I'm only going to talk about the north. Just close to the equator, this first rolling cell is called a Hadley cell. Okay, near the poles, we have another rolling cell, and this is, of course, called the polar cell. And in between the two, we have a very interesting and complicated cell called the Ferrel cell. All right, I'll talk a little bit about the Ferrel cell because it has a big effect on our story of a hurricane. But let's just look at this for a minute and see what's happening. As in with the skillet, we've heated the bottom of the skillet to a high temperature, not to boiling yet, but to a high temperature. And heat is being convected from the bottom of the skillet to the top of the skillet. Now, what does that mean? It means a different mechanism than the one I described, which was called thermal conduction. A different mechanism kicked in, and it's taking place here. Basically, this random energy is being carried on the wind rather than diffusing through the bottom of the atmosphere to the top. So we've created a wind that is picking up hot blobs of atmosphere, transporting it to the top of the atmosphere where it cools. And it transports its heat, this random motion of molecules, to the top of the atmosphere. So heat is carried by the wind from the bottom to the top of the atmosphere, but it makes this rolling motion, and so the heat, before it's completely dissipated, gets transported northward. And then it comes back down, the wind comes back down, the heat has been transferred, it's cooler back down here, the wind travels along the surface of the Earth, heating and heating and heating again, until it gets here, and it goes back up and does the cycle over and over again. Okay. Now, the same is true with the polar cells. Same thing, It moves heat from the equator side towards the pole. The Ferrel cell, the middle cell, is really quite different. Heat transfers the wrong direction. Second law of thermodynamics says heat should go from the hot equator to the cold pole, right? That's not what's happening here. It's going the other direction. And it has to go the other direction because the wind is coming down here and it's going up here. So that's the only way this cell can spin in order to get, be consistent with having 3 cells here. So heat is going the wrong direction, and this is in part responsible for the less stable weather that we see in our temperate climate. The United States is under here, right under here, under the Ferrel cell. Okay? Down here at the equator, it's very stable. You've got these steady trade winds. Arctic Sea, calmest sea on the planet. There's no weather up there. All the weather is right here under the Ferrel cell, or most of the weather. But, I'm a physicist, and we like things simple. And so the first question a physicist asks is, why isn't there just one cell? Why do you have this extra complication here? Why can't you just have one cell that starts at the equator, rolls all the way up to the pole, and goes back again? Then you don't have to need this extra order here, this extra second law violation apparently kind of problem we have. Okay, so I'm going to pause a minute and get a drink of water before I go into the answer. Does anybody have any idea? Exactly. You can't have one cell. You have to have about 3 because the Earth's rotating. When you're on a sphere and it's rotating, there's a force that acts upon moving things like wind. It's called the Coriolis force. And it's a fake force. It's not a real force like gravity, or it's only an apparent force because we happen to live on a spinning ball. And to visualize it, where this force comes from, let's do a little Gedanken experiment, a thought experiment. Suppose we're standing exactly on the North Pole, okay? And we take a ball and we throw it south. Well, we're standing on the North Pole, every direction south, okay? But we throw it south, towards the South Pole. All right, what happens? We throw it, the ball's in the air, but while the ball's in the air, the Earth is still rotating. So when the ball lands, it looks like some force moved the ball to a direction that wasn't straight down towards the South Pole. So you follow me there? You stand on the South Pole, throw a ball south, okay, ball's way up high, Earth's rotating, it lands over here, you thought it was going to land over there. Okay, so this is called the Coriolis force, and basically what it does is, in the northern hemisphere, it makes wind curl to the right, like this. So wind, no matter where it is, in the northern hemisphere, is going to curl to the right, if you're looking down on the surface of the Earth. Okay, and in the southern hemisphere, it curls to the left, of course. So if you ask the question, if we take this wind and start sending it to the North Pole, this Coriolis force is going to turn it to the right. And you ask the question, how far can it go up towards the North Pole before it's completely turned to the right and not heading towards the North Pole at all? Turns out it's about this far. Right? Same here. You're heading towards the North Pole, the Coriolis force picks up right here, and you can reach the North Pole with one swirl of wind. And so and same's true even in the Ferrel cells. So you can't have one cell because it's broken up by the rotation of the Earth. You have to have in this case 3 cells, in order to make it happen. And that's what's causing this strange, this funny backwards cell, the Ferrel cell right here, and it's what causes most of our weather in the temperate zones. All right. Well, okay. So this creates our prevailing winds. So here you see at the surface of the Earth, let me just back up 1 second here and show you what I'm talking about. At the surface of the Earth, down here, say in the Ferrel cells, the wind is going from the equator towards the poles, and up top it's going from the poles to the equators. So near the surface of the Earth, we get our prevailing winds, and the Coriolis force turns the winds to the right, and so for the Ferrel cells, you get this kind of westward to eastward flow of air. But down near the equator, you're under the Hadley cell, and so the flow is in the opposite direction because the wind is flowing from north to south in the opposite direction as the Ferrel cell. And then at the poles, again, you get a trade wind-like behavior. All right. So here we go. What's happened? We have this, as we increase the temperature from our simple little atmosphere, we increase the temperature. Suddenly, it happens all of a sudden. That's why it's called an instability. And that's why I associate it with extreme social events that I talked about earlier. It's called an instability. But suddenly, this whole structure of the atmosphere changes and these global wind patterns appear. Okay, so that's great. And, you know, as a physicist again, the next question I ask is, well, what happens if you make the temperature even hotter? Right? All right, let's see. Well, what happens is the next thing. It's like in your kitchen, as the skillet gets hotter and hotter, first you see nothing, then you see the rolling, then you see boiling. Well, you don't see boiling exactly in the Earth's atmosphere, but it's something similar to boiling. You see hurricane formation as you increase the temperature even more. Okay? And so, once again, like the onset of the Rayleigh-Benard instability, hurricane formation happens suddenly. It happens all of a sudden as the temperature is raised. All right, so what are the conditions? Well, the first condition, as I say, is temperature. When the temperature of the water near the equator, not at the equator, but near the equator, off the coast of Africa, say, gets up to about 78 degrees, 78 or 80 degrees, down to 1 meter in depth in the ocean, then that's one condition for the formation of a hurricane. If it's 60 degrees, you're not going to get a hurricane. 78 or higher, you're going to get the possible formation of a hurricane. The next condition you need for a hurricane is that the Coriolis effect, the Coriolis force, must be in effect. Now, the Coriolis force isn't the same everywhere on the surface of the Earth. You know, at poles, it's very, very strong force. At the equator, there's no Coriolis effect at all. I mean, you could think about this or look it up on Wikipedia. But at the equator, there's no Coriolis effect at all. So you cannot form a hurricane at the equator. But if you go 5 degrees from the equator, then the Coriolis effect gets large enough that it can play a role in the formation of a hurricane. So 2 conditions so far. Temperature, 78 degrees for a meter in depth, and you have to be more than 5 degrees from the equator to form a hurricane. Now, the third condition is interesting and unique, and also has social analogs. And this is the random trigger. It says, if you want to predict where the hurricane's going to happen, well, you can say it's in this area where the water temperature is high enough and the Coriolis effect is strong enough. But then you say, where in that big region is it going to happen? It's going to happen where there's a very localized low pressure area. And this can be anywhere. This is why we call it the random trigger. It could be anywhere in that area that satisfies the other 2 conditions. What happens when you have all these conditions satisfied is that the low pressure, here's a low pressure area, here's the higher pressure area out here, higher pressure area out here. This low pressure causes wind to move from the high pressure area towards the low pressure area. It's just the pressure pushing the wind. Okay. But what happens is that because of the Coriolis effect, the wind is bent to the right in the northern hemisphere. Here it's seeing bent to the right. And so the red lines are the forces due to the pressure gradient. And the green lines are the Coriolis effect on the wind after it's already turned. And we see these 2 forces balance each other out. And what happens is the wind starts going around in a circle like this, in a cyclone. Okay, so this is the formation of a hurricane, in the northern hemisphere. And there's something terribly, terribly wrong with this picture. And what is it? The wind is going around this way. It's going the wrong direction. If the wind were only propelled by the Coriolis effect, it would turn to the right. But because of this pressure effect, this low pressure effect, and this picture I've drawn, the wind turns to the left in the northern hemisphere. So I have a little story. It's an aside. I hope I have enough time. Yeah, I should have enough time. It's an aside. It's a physics story, and we physicists have an odd sense of humor. But in the old days, people were trying to understand if light had momentum. Whether if you bounce light off something, it would impart a force to that object. And so what happens is the people in the lab, you've seen these in toy stores, but they took a little radiometer that's called, put some vanes on a little stem so that the stem could rotate. On one side they painted white, one side they painted black, and put it in a little jar. You've seen these things, they go round and round when they're in the sunlight. Well, the idea was, a light wave would bounce off a white surface because white doesn't absorb light, but it would be absorbed by the black surface, because black absorbs light. It's as simple as that. And so the change in momentum of the light would be twice as great if it struck the white side than the black side. So sure enough, the people got in the lab, they built this device, and for the first time, before it was in toy stores, it started spinning, right? And so they had a party, right? Yeah, it was a great achievement. They broke out the champagne and whatever's the equivalent of pizza around 1900. And we're starting to have a party until one of the guys walked up to the thing, you know, was going and says, you know, this is spinning the wrong direction. So what's really happening is in air, what's happening is the light is coming in, it's hitting the black surface. The black surface is heating up the air around it. The light's bouncing off the white surface. That air is not heating up. So it's the air, because it's hotter, has more pressure, is pushing the radiometer around like this when they thought it should be going around like this. And so they said, well, if there were no air there, no air in the radiometer, then it should go the right direction. So they evacuated the cylinder, the device, took all the air out so it was in a vacuum, and sure enough, the radiometer turned around and flipped the other direction. Okay. So that's a humorous aside. That's what we guys call a joke. But something similar is happening here. And once again, it's the pressure, it's the atmospheric effect that's causing this radiometer to go in the wrong direction. Now, of course, what's happening is the air at the bottom is coming into the cyclone, and it's traveling up to the atmosphere, carrying its heat to the top of the atmosphere, and then the wind is going the opposite direction, and now the Coriolis effect and the pressure effect are aligned rather than opposed to each other. And so at the top of a hurricane, the wind goes the right direction. So at the bottom it's going like this, at the top it's going like this. So, you know, check that out in your pictures. Okay, so, all right, this is great. We've talked about how heat gets from the bottom of the atmosphere to the top of the atmosphere in this third regime where we have this kind of boiling hurricane action. But how does heat get from the equator to the pole? How does this heating warm up the poles? The second law of thermodynamics says nature's going to try to do that. Well, let me back up to the wind. Basically, the dominant effect is that when you create one of these cyclones, the background wind, the overall global wind pattern, blows it. So if you have a hurricane form off the coast of Africa, it's going to blow west. Okay? Well, that's great. And then if it's up here, it's going to blow east. And if it gets caught right in here, that's just perfect. It goes and takes out New Jersey and New York. I mean, that's not perfect, but you know, from a scientific point of view, everything's working. But we know that many of the hurricanes formed down here actually come up in the Gulf of Mexico, where we are. And this is a long way from the Gulf of Mexico, this kind of pattern here. How do hurricanes formed down here actually get up into here? Okay, the wind's blowing the wrong direction. Okay, and the answer is something called beta gyres, which I think is such a great name. Let me, all right, so here are the tracks of hurricanes. I took 2011 because it kind of fit my story better. But here are hurricanes formed off Africa, and they're curling up right here. And every once in a while we get something come in, like this guy right here comes in and bangs up in the Gulf of Mexico. All right, so the question, if you look at these hurricane tracks, is down here, the wind's kind of blowing in a little bit southerly direction. These hurricanes should be flowing this way. But somehow it's flowing northward and getting caught in this kind of big global vortex. And then down here, you know, there's no reason that hurricane comes down here and goes up. The wind is kind of blowing downward a little bit. So what's happening is you get two additional cyclones created by a big hurricane. And these are called beta gyres, and they steer the hurricane northward. Not as strongly as the wind blows them, but still, you know, they steer it a little bit northward, and that's enough to get it into the temperate zone where these ferrocells are, and to take the hurricanes towards the North Pole. Beta gyres. And I won't go into those any deeper because I don't understand them. But this is what does it. These little stirring cyclones are taking these hurricanes up north in order to.
So is it a combined system of rotation in one direction or counterclockwise at the surface and then clockwise at the top of the tropopause?
Yeah. The way it's usually described, and this is going to not mean anything to you, and almost doesn't mean anything to me. The total vorticity of the planet has to remain constant. And if you create a cyclone, you have to create anticyclones in order to conserve that. But so that's the cheap explanation. But you can see how this happens. This is sort of like if you fly in airplanes. You know, some airplanes have at the end of the wing these little up kind of turns in the wing. Well, what's happening is the plane's going along, and it's creating vortices, and the vortices are rolling down the wings of the plane, and they're shooting off the end of the plane. Well, when that happens, you know, when the vortices shoot out the end of the planes, it puts extra stress on the wing, and so sometimes you see these vertical little devices at the end of the wings. Those are to stop the vortices from flying off the end, and to, you know, keep the wing from rattling and such. So, and you can see that sort of thing going on right here. This cyclone is like the airplane, and it's rolling these gyres off in two directions. And I'm not going to say any more because I don't know anymore. And so then the hurricanes move north. They're carrying heat from the equator up to the North Pole. But how they carry the heat is very, very interesting. You know, I told you that heat was really energy that's stored in this random motion of molecules. And so there's all kinds of energy that a hurricane has. There's hurricane, the wind blowing, it's knocking things down. There's energy in the rain. There's energy in the surges in the sea. It turns out of these, the most important heat transfer mechanism for the second law of thermodynamics is rain. A tremendous amount of energy can be stored in going from water vapor to liquid water. There's just a tremendous amount of energy there. So what's happening at the equator, water is being turned to water vapor that's hot and then goes to the top of the atmosphere and is carried along the top of the atmosphere, where it comes down to the north and condenses, cools off a little bit, condenses, starts to rain. That is where most of the energy and most of the heat of a hurricane is coming from, is the change in going from water vapor to liquid water and back again. Much more than wind, much more than sea surge.
540 calories per gram.
There's the chemist in the room. That's a big number, isn't it, Billy?
Yeah. Lord.
Yeah. So that's the trick, you know. Water, the chemistry of water also plays a very, very important part in the hurricane formation. And so the rain falls, goes in the rivers, goes underground rivers, comes out again. It's cooled off, gets dumped back into the Gulf of Mexico or the Atlantic Ocean, gets heated again, and cycle repeats. Okay. So I'm going to stop right there because that's the end of the story on hurricane formation. And what I'm going to talk about next in just a short time, 2 or 3 minutes, I hope, is what climate change is doing for this. But I'll stop here and ask if there are any questions so far. The point is, the physics of this is very interesting. It's much more complex than you would imagine, than I would have imagined. Okay. All right. So this is a climate change meeting. What does this have to do with climate change? Well, these are the CO2 levels for the last 650,000 years. So how do we know that? How can we measure 650,000 years in the past? From ice. You dig cores in ice, and you know how old the ice is from its geology. You dig cores into the ice, and you see how much carbon dioxide is mixed in, or something. Okay, so that's how you measure the CO2 levels. But within the last 100 years, there has been an extremely sharp increase in the rise of CO2. Now, CO2 forms up much, much less than 1% of our atmosphere. So the question is, who cares? So what? Well, as you all know here, I'm preaching to the choir. What happens is the CO2 forms a layer at some level in the atmosphere. And this layer, you know, the light comes in, ionizes stuff, ionizes the CO2, other greenhouse gases. Other light penetrates to the surface. This light is converted to heat light that is heat. You know, heat could be anything. Infrared light. Infrared light can't get back out through this layer, and so the atmosphere heats up. And in fact, here are temperature measurements, or actually changes from temperature of about 1880 to the present. And we see, in fact, the Earth's temperature in this short period, but still important period, has increased significantly. This period corresponds to the period in which CO2 levels have increased significantly. So what's happening is that, of course, the surface of the Earth is getting hotter, and this is putting us into this third regime, this kind of boiling atmosphere regime. And so one expects then that storms will be stronger and more frequent, more often. And of course, the National Climate Assessment guys know this picture I just talked about, maybe not in the poetic language I expressed it, but they're basically saying the same thing. You know, storms are going to be stronger going forward, and they're going to be more frequent. Yeah. Okay. Thank you.
Any other questions, Dr. Jones? Dr. Jones, thank you so much.
Okay.